We spend so much time talking about, the huge initial training for LLMs, trillions of tokens, massive cost. But maybe the real challenge, the practical one for AI systems already out there, isn't just their starting point. It's how they get smarter after deployment. How do they adapt, learn new rules, fix mistakes without constantly going back for that super expensive full retraining?
That is absolutely the key question right now in applied AI.
Mm.
And the answer really lies in something called context
It's
adaptation.
context adaptation. Okay.
Yeah, essentially it's about improving the LLM by tweaking its inputs, the instructions, the strategies it uses, maybe the evidence it looks at. Critically, you're not changing the underlying model weights.
So you're changing the prompt or the memory it has access to, not the core brain,
Right.
so to speak.
Exactly, and that has huge advantages. These contexts are, well, interpretable, you can read them. Iterating new knowledge is fast.
Cool.
And you can even share these learned contexts across different models.
Okay, makes sense. So for our deep dive today, we're looking at recent academic work introducing a framework called ACE, that's Agentic Context Engineering. And its mission, as I understand it, is to tackle some really fundamental flaws in how LLMs currently use their working memory, their context. We're talking about problems serious enough to have names, brevity bias, and something called context collapse.
Yes, and these aren't minor issues. They point to basic problems in how we've been trying to get LLMs to self-improve. Let's start with brevity bias.
Okay.
Most of the existing ways people try to optimize prompts, things like GP genetic programming for prompt adaptation, they often really push for conciseness. Keep it short.
Right. That seems logical, doesn't it? Shorter prompt, cheaper inference, faster response.
It seems logical, but that focus on abstraction, on boiling things down, it actually becomes a failure mode for complex tasks. Think about autonomous agents or applications needing really deep, specific knowledge. Success there doesn't come from a neat little summary.
No, you need the details.
Precisely. You need detailed heuristics, specific instructions on how to use a tool correctly, maybe a list of failure modes it's run into before. If the optimizer forces all that rich detail into a short summary because it's prioritizing brevity, well, the crucial stuff gets lost. Performance drops.
Okay, so brevity bias is like oversimplifying. What about context collapse? That sounds much more dramatic. What happens there?
Context collapses. Yeah, it's a more severe problem. It happens when the system relies on the LLM itself to rewrite its entire strategic memory, like all at once, every time it tries to adapt.
Wait, rewrite everything from scratch each time.
Pretty much. And as that context grows, maybe it's learned hundreds of specific rules or error cases, the LLM start to struggle to compress or synthesize all of it effectively.
Right, and we know large LLMs, when faced with summarizing really long, complex text, they can sometimes, well, they can hallucinate, or in this case, just aggressively shorten things.
Exactly. They hit a kind of cognitive bottleneck. They default to summarizing way too much, and that leads to this dramatic, sometimes catastrophic loss of information. They essentially forget everything they just figured out because they were told to rewrite their own history.
And this isn't just theoretical, right? The sources, they point to a really specific example from the App World Agent benchmark.
Oh, absolutely. It's a striking case. The system's context size just plummeted at adaptation step 60. Its accumulated knowledge, its playbook, was around 18,282 tokens. Pretty detailed. And its accuracy was decent, 66.7%.
Okay.
But then the monolithic rewrite kicked in. The LLM tried to synthesize all that down. The resulting context, just 122 tokens.
Hold on. From over 18,000 tokens down to 122. That's basically wiping the slate clean. Why would it do that?
It's like a pathological outcome of asking it to do too much synthesis on too much information, maybe combined with those older optimization methods pushing for brevity. And the impact was immediate. Accuracy crashed to 57.1%.
Wow. And that's actually worse than the baseline accuracy without any adaptation, which was, 63.7%. So the adaptation process actively made the agent dumber.
It did. It literally forgot useful knowledge. And this really highlights the philosophical shift that ACE brings. The idea is context shouldn't be treated like these short throwaway summaries. It needs to function like a comprehensive, evolving playbook, like a detailed field manual.
An evolving playbook. I like that.
Yeah. The insight is that LLMs actually often do better when you give them longer, more detailed context and let them figuring what's relevant at the time they need to act, rather than forcing this constant lossy rewriting process.
Okay, so ACE, Agentic Context Engineering, is built to prevent this collapse, to manage this evolving playbook. It works for system prompts like offline adaptation, and also for agent memory during runtime, online adaptation.
Right. And the architecture itself is interesting. It kind of mimics how humans learn. We experiment, we reflect on what worked or didn't, and then we consolidate those lessons. ACE uses 3 specialized modular roles, different LLM instances, essentially, to handle this. This avoids having one single model trying to do everything, which was part of the bottleneck problem before.
Okay, break down those roles for us.
First, there's the generator. That's your main LLM agent doing the work. It takes the user's query, looks at the current playbook, and produces, the reasoning steps, the tool calls, the code.
Standard Asian stuff.
Pretty much. Then comes the really critical part, the reflector. This is where the learning happens. The reflector looks at what the generator did and critiques it using actual feedback. This could be execution traces like what commands actually ran, did they error out, or maybe results from unit tests, or even just simple success-failure signals from the environment it's interacting with.
So it's not just guessing. It gets concrete feedback on the generator's actions. And its job is to turn that raw feedback, like a failed script, run into something useful.
Exactly. It distills real insights. It doesn't just say, code failed.
Yep.
It tries to figure out the root cause, like, the failure was because it used the wrong API endpoint for pricing, or maybe it missed the authentication step. It creates these structured little pieces of knowledge.
Got it. Structured failure analysis. And the third role.
That's the curator. The curator takes these distilled insights from the reflector and figures out how to integrate them into that evolving playbook. And this is where ACE tackles context collapse directly, using its first key innovation, incremental delta updates.
Delta updates. Okay, so delta meaning change.
Precisely. Instead of rewriting the whole playbook, which we saw leads to collapse, AC treats the context as a collection of structured, itemized bullets. Think of them as individual strategy points, concepts, known failure modes, specific rules. The curator only produces small, compact delta contexts. These are just the localized changes, adding a new bullet, modifying an existing one, maybe deleting an old one.
It sounds almost like using Git or version control for knowledge. You're not rewriting the whole code base, you're just applying a targeted patch.
That is a perfect analogy. It's exactly like that.
Yeah.
And crucially, merging these small delta updates into the main playbook is done using simple, deterministic, non-LLM logic.
Ah, so it's not asking the potentially unreliable LLM to do the integration, it's just rule-based merging.
Right. Simple rules like append this new bullet point here or replace bullet point #57 with this updated version. This avoids hallucination during the integration step and makes sure the knowledge is added or updated with high fidelity. It preserves the existing useful stuff.
Okay, so that definitely tackles context collapse by avoiding the big rewrite. But what about the other problem, brevity bias? If you're always adding new billets, doesn't the playbook just get massive and unwieldy? How do you manage the accumulation?
Good question. That's handled by the second key innovation, the grow and refine mechanism. It's basically knowledge hygiene. The grow part is that the system is designed to accumulate knowledge with new insights from the reflector are constantly appended. It embraces detail. But the refine part prevents it from becoming just a giant redundant mess. It periodically performs deduplication and a kind of soft pruning.
How does it do the refining without losing detail, like the brevity bias problem?
It uses semantic embeddings, basically vector representations of the meaning of each bullet point. It can then run fast similarity checks to find items that are highly overlapping or redundant. Instead of asking an LLM to summarize and risk losing info, it identifies near duplicates based on meaning and can consolidate them or maybe prune less frequently used, older versions if needed. So the playbook stays comprehensive but avoids unnecessary repetition.
Okay, that makes sense. It's about managing redundancy smartly, not just cutting for length. Can you give an example of what might actually be in this playbook?
Yeah, the sources give some great examples. Under a section like useful code snippets, you might find a specific Python template, like efficiently using default list for aggregating artist data from some API. Or under troubleshooting and pitfalls, you might find a very concrete rule like, if the initial login attempt fails using the email address, retry using the associated phone number as the username because of that legacy system quirk. It's that level of granular detail that gets lost with brevity bias, but is crucial for robust performance.
That really paints a picture. Very practical, specific guidance. Okay, so the mechanics seem sound. How did it actually perform when they tested it?
They tested it across 2 pretty challenging areas. First, complex agents. Using that app world benchmark we mentioned, it involves multi-step reasoning, using tools, generating code. Second, on domain-specific reasoning, specifically financial analysis tasks like FINER and Formula, which need deep knowledge of things like XBRL reporting standards.
And the results. Did ACE actually make a difference compared to other methods?
Yes, quite a significant one. ACE consistently did better than the baselines, things like just providing examples in the prompt, ICL, or that GPA prompt optimizer we discussed earlier.
What kind of gains are we talking about?
On average, something like plus 10.6% improvement on the agent tasks and plus 8.6% on the domain-specific benchmarks, at least when they had ground truth labels available for the offline adaptation phase. But the agent result is probably the most eye-catching, especially the comparison with proprietary models.
Ah, right. Tell us of that comparison. That sounds interesting.
So they took ACE and used it with a smaller open-source model, DeepSeek v3.1. The agent setup was React plus ACE, and this combination achieved an average performance score on AppWorld that matched IBM's CUGA, which is a top-tier production agent running on GPT 4.1.
Matched GPT 4.1 performance with an open source model just by using better context engineering. That's huge.
It really is. It suggests that smarter context management can significantly bridge the performance gap, often attributed purely to model size or proprietary training data. It's a big win for making powerful AI more accessible.
And I think I read it got even better in the online setting.
It did. On the harder test challenge split of AppWorld, which focuses more on adapting to novel situations during runtime, the React plus ACE setup actually surpassed the performance of the IBM CUGA agent. This really demonstrates that this kind of continuous, structured learning using the playbook can make a smaller model strategically smarter in action than a larger model relying mainly on its static base knowledge.
That's impressive. What about learning without perfect supervision? We often assume self-improvement needs labeled data.
That's another compelling finding. ACE showed it could improve substantially using only natural feedback signals from the environment, basically. Just knowing if the code it generated ran successfully or failed, no human labels needed. Using just that success-failure signal on AppWorld, it still achieved a 14.8% average improvement over the baseline. That's really key for building truly autonomous agents that can learn in the real world without constant human oversight.
Okay, so it makes agents smarter, even learning on their own. But what's the catch? Does all this sophisticated context management add a lot of overhead? Latency, cost. Long context can be slow and expensive.
That's where the design choices, particularly the incremental delta updates, really pay off. Because you're avoiding that massive overhead of rewriting the entire context every time, the efficiency gains are dramatic.
How dramatic? Got any numbers?
Yeah, compared to other adaptive methods, ACE showed an 86.9% lower latency for the adaptation step itself on average. In the offline setting on AppWorld, it needed 75.1% fewer expensive trial and error rollouts compared to GPay. And in the online setting, comparing to a method like Dynamic Cheatsheet on the financial tasks, they saw a 91.5% reduction in latency and an 83.6% reduction in the actual token dollar cost.
Wow, so it's not just better, it's significantly cheaper and faster to run the adaptation process itself.
Exactly. Self-improvement is great, but it needs to be efficient to be practical. ACE seems to deliver that by being surgical with its updates.
This really feels like we're moving beyond just basic prompt engineering towards sophisticated context management as a core part of AI systems. And you're saying this is practical now partly because the infrastructure for serving these long contexts is getting better.
Absolutely. Techniques like KV cache reuse and compression in modern LLM serving systems make handling these larger, evolving playbooks feasible in production. So, context adaptation like ACE offers this flexible, efficient path for continuous learning, often as an alternative to much heavier fine-tuning. But there's another advantage, especially important for responsible AI: selective unlearning.
Selective unlearning. How does a playbook structure help with that?
Because the knowledge is stored as these distinct human-readable bullet points, a specific rule, a strategy, a recorded failure, you can actually go in and target specific pieces of information for removal. If a domain expert identifies a strategy that's now outdated or incorrect, or maybe contains private information that needs to be removed under regulations like GDPR.
You can just delete that specific bullet point.
Precisely. You can perform surgical removal of knowledge without affecting the rest of the playbook or needing to retrain the whole model. That level of precision and interpretability is incredibly valuable for maintaining trust and compliance, compared to trying to erase something from the opaque weights of a neural network.
That transparency is definitely key. Okay,
Yeah.
so it's powerful, efficient, more interpretable.
Yeah.
But the source material does highlight a key limitation, right? It's not magic.
That's true, and it's an important caveat. The effectiveness of ACE, particularly the reflector module, really hinges on the quality of the feedback it receives.
Right. Garbage in, garbage out, potentially.
Sort of. If the system is operating in a domain where the feedback signals are noisy, ambiguous, or just plain scarce, if it's hard to tell if an action truly succeeded or failed, or why, then the reflector might distill incorrect insights. And if that happens, the curator could end up polluting the playbook with bad strategies or faulty knowledge.
Okay, so the reliability of the learning loop depends heavily on the reliability of the success-failure signals it gets from its environment or task.
Exactly.
Which leaves us, and you, the listener, with a really interesting question to think about as these self-improving systems become more common. In domains where clear, objective, binary feedback is hard to come by, think about maybe creative writing or generating high-level business strategy or even political analysis. How do we ensure that these context-based learning systems remain trustworthy? How do we prevent them from just reinforcing their own mistakes or biases when the feedback loop itself is inherently fuzzy?
You know, one of the biggest holy grails in AI is getting these systems to learn on the fly, from experience, just like people do. But that's always been incredibly hard, usually requiring a complete and super expensive retraining of the model. Well, today, we're diving into a new framework that might just crack that code. It's called Agentic Context Engineering, or ACE, and it's a whole new way to think about building self-improving AI.
So here's our game plan. We'll kick things off with how AI learns on the job right now, and a massive problem it runs into called context collapse. Then, we'll look at how a new kind of AI playbook is built to fix it. After that, we'll see how this solution holds up when we put it to the test, and finally, we'll talk about what this all means for the future of AI.
All right, let's get right into it. First up, the core challenge here, which is all about getting AI to learn continuously. This is really the bedrock for understanding the problem that ACE was built to solve.
And this really boils down to one giant question that's been hanging over the entire field. Retraining a massive language model from scratch is just insanely expensive, both in terms of computing power and money. So researchers have been hunting for smarter, more agile ways for an AI to adapt and get better.
For a lot of folks, the go-to answer has been this thing called context adaptation. The idea is, instead of doing major surgery on the AI's brain, what we call its model weights, you just feed it new information right in its input prompt. Seriously, think of it like handing an employee a new training manual or a cheat sheet before they tackle a new project. It's way faster, way cheaper, and so much more flexible. But, and this is a big but, this method has a pretty dangerous dark side.
And that brings us to the villain of our story, a critical, almost catastrophic flaw in how a lot of AIs try to learn from their mistakes.
There are actually two culprits here. The first is something called brevity bias. This is where the AI, in an attempt to be efficient, just oversimplifies its own notes and loses all the juicy, expert-level details that actually matter. But the real monster, the one we're focused on, is context collapse. This is when an AI is asked to update its memory, and it decides the best way to do that is to summarize everything. And in one fell swoop, it basically erases almost everything it's ever learned.
So the very act of trying to get the AI to consolidate what it knows can just blow up in your face. This whole idea of rewriting its memory all at once is just fundamentally unstable. Instead of getting smarter, the system can suffer from what they call catastrophic forgetting.
And this graph, wow, it just lays it all out there. On the vertical axis, you have the size of the AI's memory, measured in tokens. You can see it's learning, it's growing steadily for 60 steps, getting up over 18,000 tokens of knowledge. Its accuracy is a decent 66.7%. And then, step 61 happens. Boom, collapse. The AI summarizes its memory and it nosedives to just 122 tokens. Performance craters to 57%, which is actually worse than when it started. This isn't a small bug, it's a total system failure. This is context collapse.
Okay, so how in the world do you fix a problem that dramatic? Well, you need a completely new way of thinking, and that's where our hero comes in. Let's talk about the solution, the Agentic Context Engineering Framework, or ACE.
The big idea behind ACE is to completely flip the script. Stop thinking about the AI's memory as a summary that needs to be shorter. Instead, you treat it like a comprehensive, living, breathing playbook. The goal is to collect and organize detailed strategies and insights, not to compress them until they're useless.
And this isn't some abstract concept. I mean, look at this. This slide shows you what an actual ACE playbook looks like. It's a real, structured document. It has hard-won rules. It's got useful code snippets all ready to go, and it even has troubleshooting tips for common problems. It's a practical, detailed instruction manual for the AI, written by the AI.
Now, the architecture of ACE is just brilliant, and it's built around a simple idea: division of labor. Just think of it like a professional sports team. First, you got the generator. That's your player on the field, actually trying to get things done. Then you've got the reflector. That's the coach on the sidelines, watching the game, analyzing what went wrong, and figuring out the lessons. And finally, you have the curator, the team's librarian, who takes the coach's notes and meticulously updates the official team playbook for the next game.
And here's the secret sauce. This is how ACE avoids that catastrophic memory loss. Instead of telling the AI, hey, rewrite the whole playbook from scratch, the curator makes small, structured, incremental changes. It adds a new tip here, tweaks a strategy there. This approach means valuable knowledge is always preserved and built upon, never, ever thrown out in a disastrous attempt to summarize.
Okay, this all sounds amazing in theory, right? But the billion-dollar question is, does it actually work? Well, let's head into the arena and see how ACE performs when it's put through its paces on some really tough benchmarks. The results are, frankly, pretty stunning. This chart shows you the performance boost you get with ACE across 3 totally different areas. And as you can see, in every single domain, ACE provides a massive lift over already strong methods. It's not just a one-trick pony. This thing is robust.
And to put a hard number on that, on average, for these complex agent tasks, ACE delivered a 10.6% performance gain. Now, in the world of AI benchmarks, that is a huge, huge leap forward. That's a game changer.
But this slide is my favorite part. It's a total David versus Goliath story. This is the leaderboard for a super difficult benchmark called AppWorld. At the very top, you have this massive production-grade system from IBM running on GPT-4.1. And right there, tied with it, is a much smaller open-source model that's been supercharged with the ACE framework. That is just incredible. It shows that a smarter learning strategy can let a smaller player punch way above its weight.
And get this, it's not just about being more accurate. ACE is also wildly more efficient. We're talking about the time it takes to learn, the adaptation latency, being cut by almost 87%. It's cheaper, too, requiring 75% fewer rollouts, which is a proxy for compute cost, and the actual dollar cost for tokens down by over 83%. So it's better, faster, and cheaper. That's the trifecta.
Okay, let's zoom out and bring it all home. What are the big picture implications here? Why does a framework like ACE really matter?
Well, for starters, ACE gives us a clear, practical path towards AI systems that can genuinely get better on their own, through experience. It makes AI learning way more efficient and scalable, which opens the door to continuous on-the-job learning in all sorts of real-world apps. And because the playbook is just a text file, we can actually read it and understand what the AI has learned. This even means we can do selective unlearning. Just go in and delete a rule if it becomes outdated or wrong. That's amazing.
And that really leaves us with this final, powerful thought. We're shifting from AI that just follows our instructions to AI that learns, adapts, and literally writes its own, constantly improving playbook for success, all in real time. The question is no longer if AI can learn on the job, but how quickly it will master it, and what incredible new things will become possible when it does.